Today's topic is Hess's law. Hess's law is going to be another way that we use to calculate molar enthalpies. And the main thing is it's going to allow us to treat reaction equations almost like algebraic equations, where we can turn them around and multiply them and divide them. It's going to make use of the law of conservation of energy. And to give you a quick example of how those two things can be combined, take for an example making of water using 1 mole of hydrogen, half a mole of oxygen to make 1 mole of water. The energy that would be involved in that reaction, as you can see, is roughly 242 kilojoules exothermic. So energy would be coming out in that reaction. Now, if I made 2 moles of water, so 2 moles of hydrogen, 1 full mole of oxygen to make 2 moles of water, then I would have double the amount of energy. Double the stuff, double the energy. And if I took water and broke it down into hydrogen and oxygen gas, then the amount of energy that would go in an endothermic process would be equivalent to the amount of energy that came out in the exothermic process. So that's the basics on how we're going to treat reaction equations, almost like algebraic equations, in doing Hess's law. Well, why would you bother? Well, the main thing that Hess's law is used for is to come up with, to calculate enthalpy for reactions that we cannot actually do, or at least are very difficult for us to do for real. So what we would do is we would have other reactions that we combine to come up with let's say a roundabout or an indirect way to do this. All right, so let's look at an example. Here's a typical kind of question that you would have. You'd be asked to come up with a molar enthalpy for some process. In this case, the formation of butane. And as you know, a formation reaction is making of 1 mole of stuff, so in this case 1 mole of butane, from the elements, carbon and hydrogen, in their standard state. So you see carbon is a solid and hydrogen is a diatomic gas. And we're asked to come up with that. Now, little aside, but if you were to take 4 moles of carbon and 5 moles of hydrogen and react them together, you would not make butane. So this particular reaction works on paper, but would not work in real life. So how do we get the number? Well, we use Hess's law. You'll always be given certain reactions to use. So in this case, we're told we're told the combustion of butane. So butane reacted with oxygen to make carbon dioxide and water. We are told the combustion of carbon. Carbon reacted with oxygen to make carbon dioxide. And we're told that if we take oxygen and hydrogen, react them together to make water, we get that number. Slightly different from the one I showed you because that one was rounded off and this was not. Those 3 reactions we can combine to calculate the molar enthalpy of formation for butane. How do we do it? Well, we start with our reaction as our target. And then what we're going to do is we're going to use the other ones, manipulate them so that when we're finished, we have 4 carbons plus 5 hydrogens and to make butane. So what I like to do is I like to pick something to start with. So what I did was I decided to start with 4 carbons. In other words, I need carbon as a reactant. So I look through my list of reactions and I find that reaction number 2 has carbon as a reactant. Now I multiply it by 4. And if I multiply the second reaction by 4, I will have 4 carbons and 4 oxygens making 4 carbon dioxides, but most importantly, 4 carbons. Now, I'll also multiply the energy term by 4, so 4 times the -393. Now, of course, that does 2 things for me. It puts the carbon where I need it to be, but it also obviously puts carbon dioxide in my overall reaction. So I now am going to try and eliminate that 4 carbon dioxide. So it's almost like I had a reaction that produced carbon dioxide. Now I'm going to try and use it, consume it in some other reaction. So I look through my reactions trying to find carbon dioxide. And I find it in reaction number 1. Now reaction number 1 has carbon dioxide as a product. I actually want it as a reactant. So I take reaction number 1 and I reverse it. And I've indicated that by -1. I reverse that reaction and that puts 4 carbon dioxides in the reactant position. Not only that, but you'll notice at a happy accident, it gave me butane as a product, which oddly enough is what I'm looking for. It also, though, gave me water as a reactant. So that 5 moles of water I have to somehow eliminate. In other words, if I think about carbon dioxide being produced and then right away being reacted out, I now am trying to find some water to be the reactant. So I'm going to find a reaction that produces water. And I can find water in my reaction number 3. Now, in order to get 5 moles of water, I'll have to multiply that reaction by 2.5, 2.5. And of course, I'll do the same thing to the energy term. So when I do that, I get 5 moles of hydrogen as a reactant, 2.5 moles of oxygen, and on the product side, this is why I did it, my 5 moles of water. Okay. Now, not only that, but it gave me 5 moles of hydrogen as a reactant, which, have the accident again, is what I wanted. It also gave me oxygen. Now, the first thing I'm going to do before I worry about the oxygen is if I have carbon dioxide as a reactant and a product, same state, same number of moles, I can cancel that out. Same thing with the water. Remember, I was trying to get 5 moles of water as a product. That was so that I could cancel it out with the 5 moles of water that were a reactant. What about the oxygen? Well, I've got oxygen in a couple of spots. I've got 4 moles of oxygen and 2.5 moles of oxygen on the reactant side of those 3 reactions. That gives me a total of 6.5 moles of oxygen. And again, happy accident, I have 6.5 moles of oxygen on the product side. So between the 2 reactant oxygens and the 1 product oxygen, I've got enough that I can cancel out all the oxygens. So when I'm finished, all I have are the 3 things in the target, the 2 reactants and the 1 product. Well, now what? Now I add up all those things, and of course adding them up is where the canceling out happens. But I also add up the energy terms. Whatever I did to the reaction, I do the same thing to the energy. Multiply it by 4, change the sign, right? Reverse it, multiply by my -1, multiply by 2.5. And then I'll take all those energy terms, I'll add them up, and I have, in this case, minus 125.4 kilojoules of energy, exothermic. Okay, a lot going on, but it's actually fairly simple. And a couple of tips that I can give you, a couple of suggestions to make things go a little bit smoother and more reliably. Number one thing is you can only cross out things if they are exactly the same. And that means they have to have the same state and the same chemical formula. You cannot cross out liquid water with gas water. You cannot cross out the hydrogen from water with a hydrogen from something else, even a hydrogen on its own. They must be exactly the same before you can cross them out. And also, one has to be in the reactant side, one has to be in the product side. And then finally, number 1 thing, I guess number 2 things, I already gave the number 1 thing, is be systematic. It doesn't matter if you work through the reactions 1, 2, 3, 3, 2, 1. It doesn't matter if you, what I did this time was I started with putting a reactant where it needed to be. Find a system that works for you and then stick with it. So you'll notice on the one that I did not multiply the 4 times the energy term. I said I was going to, but I didn't until I was doing the final answer. Same thing with the negative sign. I'll write it down to make sure that I remember, but I don't usually do the math until I'm doing all the math. Let's take a look at another one. And we're going to come up with the enthalpy of formation for, this is called diborane. 2 borons, 6 hydrogens, B2H6. Given those reactions. Now, I'm going to really suggest that you copy this down, you pause it, copy this down, and then work it through on your own, and then see if I can be 1 step behind you the whole time. Or do it completely, and then check how I did it, if we ended up doing the same thing overall. Okay? All right, here we go. So, my target reaction is that formation reaction, making 1 mole from the elements in their standard states. Boron is a monatomic solid, means no diatomic, just boron atoms. And hydrogen is a diatomic gas, as we know from before, making diborane, or B2H6. So, my plan, this time I'm going to do things a little bit differently. I'm going to put the product where I need it to be. So I first put the product where I needed to be, so I took reaction number 2 and I cut it in half. And whatever I do to the reaction, I do the same thing to the energy term. And actually I take that back, I put a reactant where I needed it to be. It happens. So 2 borons are in place. I also then have B2O3, boron oxide, diboron trioxide, I guess. So now I'm going to try and eliminate that. So I need B2O3 as a reactant. And I'll get that by reversing reaction number 1. When I reverse reaction number 1, I get the B2O3 as a reactant so that I can cross them out. I also get my product where I need it to be, in the product position with the right balancing coefficient. Now I've got some oxygen there, but I'm going to leave the oxygens for a second. I'm going to focus on, well, that oxygen, I guess, but right now I'm going to focus on the water. Okay, so identify the oxygens that are there. I could start to cross that out a little bit, but hang on, I'm going to let it ride for a minute. I'm going to focus on the water now. So 3 moles of water. There's no water in my target reaction, so I have to eliminate that water. Right now the water is on the reactant side. I need it on the product side. So I take reaction number 3 and multiply it by 1.5. When I do that, I get my 3 waters on the product side so that I can now cancel them out. I also got 1.5 moles of oxygen also on the reactant side. So now I've got 1.5 moles in the first line, 1.5 in the third line, and that's going to balance out nicely or cancel out nicely with the 3 moles of oxygen that are on the product side, so they can all be canceled out. Not only that, but I also have 3 moles of hydrogen in the reactant side. So in other words, the only thing that I have not eliminated are the 2 reactants and the 1 product that I need to have. So Hess's law of summation is add them all up, do the thing you need to do to the energies, do the math, that is, add them all up, and we end up with our target reaction, and now it's an endothermic reaction to the tune of about 35.5 kilojoules of energy. One last comment. It, again, does not matter whether you have 3 reactions, 5 reactions, 7 reactions. It doesn't matter if you've got 2 reactants, 2 products, or any combination. If you are systematic and if you're watching the states and you're making sure that whatever you need to eliminate will be on the opposite side of the arrow, Hess's law is a little slow, sometimes a little tedious, but actually very, very simple. We'll try a bunch in class, you'll have lots of practice, and we'll see you later.